Привет, как дела? Yes. The rest of the talk I will give in English. I will talk about GraalVM. I'm a senior research director at Oracle, and I'm the leader of the GraalVM project. Maybe some of you have already heard about it. I will not go a lot of detail about GraalVM itself, but I will talk about how GraalVM can help your Java applications run faster. And I will talk generally a little bit about what performance for Java application means and how to measure performance, and I will give a couple examples. Yeah, so this is our safe harbor statement. I need to put it up. And so when we talk about performance, performance can have many different meanings because the question is, what is performant? Like, what type of thing are we measuring when we talk about performance? And there's a lot of mistakes made, actually, where people think they measure a certain type of performance, but then they measure other things. And there's various categories of performance that you can think of. One is startup performance. The other is warm-up performance, and the other is peak performance. Startup performance is when you measure your application sort of in the first, let's say, 500 milliseconds, like very early stage. Warm-up performance is then more like in the middle phase of the application, maybe in the first minute or a couple minutes even. And then peak performance is when your application reaches the steady state. So it runs maybe for hours, and then it reaches the final peak performance, which is the maximum performance you get out of your application. And when you measure performance of a certain application, maybe sometimes people are more interested in startup, sometimes more interested in warm-up, sometimes more interested in peak. But it's important to distinguish this when we talk about performance. The second aspect is, when we talk about performance, we can mean at least three different major things. I mean, many more, but three are the main things I think developers care about in terms of performance. The first one is throughput. It's like, how many requests per second does my web server take? How many operations per second does my application perform? The second one is latency. It's like, how quickly does my web server sort of do the next request, or how quickly does my application react to a peak load. And in web server applications, this is sometimes even more performance, more important than the throughput. And the final thing on performance is performance also can mean to use less memory. Basically, be more performant per memory that the application uses. This is quite relevant in a cloud environment where memory is very costly, and we want to deploy as many instances of the application as possible. And then finally, we can talk about sort of the minimum throughput or the minimum latency that is given by the application. We can talk about the maximum latency. That's often a metric that's relevant for web servers. Like, what is the maximum latency that a certain request gives you? And we can also talk about average latency. And similar for memory footprint, for example, we can also talk about minimum, maximum, and average. And yeah, to make matters more complicated, we can actually combine all these things. Basically, we can talk about the peak memory footprint, the maximum one, or we can talk about the startup latency, let's say. So this is just to give you a little bit of an overview of what performance can actually mean, and sort of like what of the things we could measure there. And what you care about when you develop an application, you should think kind of, what do I care about most? Or how do I value these things? Do I value more the warm-up performance? Do I value more the peak? Am I interested in latency, or does latency for my application not matter? Because depending on the answers, you will use different VM configurations, you will use different garbage collection configurations, and you might use different virtual machines altogether. So after this overview, I will talk now about GraalVM as a project, and why we think GraalVM gives performance, and what configurations of GraalVM are best for each of these possible things to get performance out. So GraalVM, generally speaking, is a polyglot virtual machine. It can run many languages. It can run all of your favorite Java and JVM-based languages like Java, Scala, Groovy, Kotlin. It can run, but in contrast to the normal JVM, it can also run other languages. It can run JavaScript. It can run Ruby, R, or Python. And not only that, with GraalVM, we also have a way to run native languages that are compiled to LLVM bitcode. So we can take C, C++, Rust programs, compile them to LLVM bitcode, and then run them with GraalVM. And we have like a special way how to do this, which is this automatic transformation of the interpreters of that language to a compiler. And if you want to know more about that part, I will not go in detail. I will not talk in detail about this in this talk. But tomorrow, Oleg Shalayev has a talk on exactly how this transformation, how this magic under the hood of GraalVM works. And then GraalVM can not only run these languages, it can run them also in different environments. It can run them in your OpenJDK platform. So this is where the GraalVM compiler is replacing the existing OpenJDK compilers. It can run also embedded in Node.js. So we can run any Node.js application with GraalVM. And there we replace Google's V8 compiler with the GraalVM compiler. We can run in the Oracle database. We have a prototype for this to run Graal directly on the data to reduce potential latency introduced by going back and forth between the database and the middleware. And finally, we can also run it standalone. And in this talk, I have a couple of demos now, and I will focus on two things here. I will focus on running Java, Scala, and Groovy via OpenJDK on GraalVM. And the second thing I will focus on running those things standalone. And if you were remembering this performance slide that I had previously on what type of performance you might optimize for, if you optimize for peak performance, maximum throughput, then our recommended configuration is to run GraalVM on OpenJDK as a JIT compiler. If you care a lot about having good startup performance and having a low memory footprint, then we recommend the standalone GraalVM native image processes that can give you this property for your application. So I was like yesterday on Twitter, somebody asked me like, can GraalVM eliminate the array creation and boxes in the following call? And it was a very interesting question, and I decided to create a live demo for that. So you have a guarantee that it's not some pre-canned content, but really fresh off the press from last night. And because in Java, often we like to use abstractions. So we like to use objects, and we create objects and store things in them. And as a Java JIT compiler, our goal is to make you able to use these abstractions without regret. So use the abstractions without having any performance losses. And one of the first things that GraalVM does as a compiler is it has the ability to remove object allocations. So we'll now go like to the first part of the live demo. And so generally, when you forgetting GraalVM, you can just go on like graalvm.org. And on graalvm.org, you will have sort of the ability to download GraalVM from the Oracle Technology Network or from GitHub, depending on which edition you're working with. So in these demos, I will use the GraalVM Enterprise Edition that I downloaded from Oracle Technology Network. And so if I download this GraalVM Enterprise Edition application, and I expand it on my disk, what I will see is something that looks very similar to a Java home directory. So this is here the GraalVM home directory. It has all of the Java commands and all of the commands like Java developers are familiar with. It has a few extra ones. Most notably, maybe there has a node command and an npm command, because it can not only run Java applications, it can also run node application. And it also has this native image command that I will use in the second demo today. But at first, it just has a normal Java command, and we can check out the version string of this. And it says, yes, so this is Java hotspot VM. So we're running here on standard hotspot OpenJDK. And we're running here GraalVM EE on the latest release candidate. And in order to measure performance, one of the best tools out there is Java Micro Benchmark Harness from Alexei Shipilev. And so I'm using this tool for the benchmark measurements. The nice thing about the tool is that it gives you this very good distinction between warm-up performance and peak performance. And it gives you sort of the performance over time of the application. And what I have here, I have a little bit, a small example here. My first example benchmark is just to set a baseline. It just returns 42, and that's the test base. So I can now, yeah, let's just make sure I have the correct, yes, I have Java as the correct version here. And I can now say, and then I can say, escape analysis test base. So this is just the baseline. This is the Java Micro Benchmark Harness. Who has never used this one? Or who has used this one? Excellent, excellent. So yeah, so this gives about 1,300, 1,500 operations per microsecond. And what I can do then with Graal is, well, what if I just create a new integer here, because I create a new object. So I kind of box the integer and unbox it. And well, if I execute this one now, it's not very surprising. The performance goes up, and it's the same performance. It's actually a little bit better here, but that's more the variability on my laptop. But it's the same performance as before. And despite the fact that I've just allocated an object and unboxed the object. This is what we call escape analysis, where the compiler is able to remove that allocation. We can make it a little bit more complex here in the next example, which is testing array. So I now put this integer into an array, and I get it out of the array again. And I again can like execute that. And well, performance stays the same. Doesn't matter. So, well, let's be a little bit more challenging to the compiler. And yeah, I got this little example here. So next time somebody asks you, you write inefficient code, you can show him this one. And yeah, and you will actually be able, let's test complex. And yeah, same performance. So inefficient code is actually very hard to spot, because this code is very efficient code. It is maybe harder to read, but from a performance standpoint, it's the same performance as this one here. So yeah, you can start to obfuscate your Java programs with GraalVM. That's great. So what if I want to really kind of make sure the object escapes, kind of trick the compiler? And for this, I have here this test sync, where I'm creating the object and I'm storing it into a static field. So this is the point where the object actually escapes sort of the compilation or the view of the compiler, because the compiler can only do the escape analysis if the object is local to the current thread. And when the compiler can no longer prove that the object is local to the current thread, the compiler has to allocate the object. And we can see this in the performance if I now see a test sync. And now Graal tries to get this better, but it's still 4x slower now, because now we actually have the allocation in the code. So this is kind of to demonstrate and show that as long as everything stays local, all of the object allocations go away. And only once you store something in a value that is not proven to be local, then the object allocation actually occurs. So there is actually a practical pattern where this matters. It's when you are returning two values from a Java object. The usual way to do this is to box them into an array. And if the compiler does not have escape analysis, then some clever programmer will allocate that array as a static field and sort of reuse the same array across invocations. But this actually makes the code slower, whereas a compiler with escape analysis, they can inline the call will be able to remove this array that's allocated for the result of the function. So this is just generally a sort of a general performance tip of like keep things local when it comes to allocations and avoid things that are stored somewhere for as long as possible. But as long as you keep things local, all of these abstractions are totally free. But yeah, let's get back to this question from the JetBrains engineer. And so this is, I have here the next example here, which is objects.hash. And so there's this objects.hash utility function. There's this utility function in objects to do equals and hash and so on. And those utility functions, I have here the implementation of those utility functions. So they are variable length argument array. So it actually allocates an array. Then it calls arrays.hashcode on it. Then arrays.hashcode will actually iterate over that array and calculate the hash code. So one would expect here that like this int, double, and long field will all be boxed. There will be a new array created, given to that method, and then somebody iterates over that array, and the result comes back. And I have here the raw version of like sort of the unboxed version that's manually written, and that one is just directly doing the hash code computation here. And if I now, let's go here, it's called objects hash dot test dot abstracted raw. Let's do raw first. So I run this with the Graal compiler, and the raw version is giving me here about 350 operations. But yeah, I was lucky on the last one, but around 400 operations. And what I can do now is I can do objects hash dot abstracted. And it's 420. It's actually, we actually got a faster run here, but it's the same speed here, about 420 operations per microsecond. So when you use the Graal compiler, you can actually use these abstractions without any slowdowns. And we can also measure here using not the Graal compiler, which I do with a -use JVMCI compiler flag. And I first do the raw version again. Yeah, so the raw version here is 440 ops. It's actually a little bit faster here. And then I can use the abstracted version. And suddenly you only have 60 operations per second. So the Graal compiler is able to remove this loop and these allocations, whereas a traditional compiler is not. And for the Graal compiler to do this, actually, it needs to unroll this loop. So it needs to see that this loop is constant, unrolls the loop, removes all the allocations, and streamlines the code. One type of thing that often gives complex patterns as well is the stream API. And for this, I have here a simple test case that is summing up values. And using stream API, you have an array of values. I'm mapping those values, I'm reducing them, and then I get the final result. So I can run this again on the Graal compiler. And this is the test simple method. And it's got 160 operations per second. And so the interesting thing on the Graal compiler is now I add a few more abstractions to it. So I do a couple more maps. Let's see how that one goes. Test complex. Yeah, and it's the same performance, actually. So despite the fact I'm using much more abstractions here, I get the same performance. And so let's see now what happens if I don't use the Graal compiler. Any guesses on how much slower it's going to be? How much? 10 times. A real optimist in the audience, I guess. Other guesses? 3 times. Yeah, that would be good, right? Let's see. So your current hotspot compiler, come on. It doesn't go higher. It doesn't go higher. All right, that would be about, yeah, about 30 times. Yes, thank you. Yes, exactly. So this shows you like how these things actually can stack on top of each other. Where you remove one abstraction, remove the next one, and this way things can stack on each other. And I'm not claiming that your average Java program runs that much faster, but there are instances where this happens. And generally, it's just the Graal compiler is able to basically make this code run the same speed as this code, which is kind of what is expected. The simple, this is without any +1. This is a little bit faster. I can show this as well. Test sum. That's just testing the sum. And so here, actually, in the test sum, the traditional compiler is quite a bit better. It's like 6x faster. And then I can here. Oh, come on. Yeah, for us, it's just the same speed, all of them. Because it doesn't matter. Yeah, and so, but we do this without special knowledge about the Stream API. Meaning, if you use a different collection library, or if you use, let's say, Eclipse collections, you will benefit from the same type of optimizations. Because all the Graal compiler does here is sort of look at these Java bytecodes and tries to do the best optimizations from them. And generally speaking, the more modern Java you're using, the more abstractions you're using. If you're using Kotlin Scala, it gives us more ability to optimize better. And that's where the Graal compiler, the GraalVM compiler, is showing the main benefits. So yes, so this the answer to that is yes. It does eliminate all of the array creation and boxes, and you can, with good consciousness, use the actual abstractions available in the JDK. All right, but apart from this better peak performance for Java applications, GraalVM also has this way to create native images, and it's very popular. So some people actually think only this is GraalVM. GraalVM has many things. One of them is the native image generation stuff. And this is a mode you can run your application, and you don't have to. You can run GraalVM just on normal OpenJDK, but you do have the ability to run via GraalVM native images. And GraalVM native images is a way to ahead of time compile Java applications. The main challenge with ahead of time compiling Java applications is that they're usually not bounded, meaning it's very hard to figure out what an application actually uses. And this is why we created a closed twirl, so-called points to analysis. It's something that's basically starting from a main method and then like simulating the program and finding out what parts of the libraries you're using and what parts of JDK are actually reachable. And by this, it's sort of expanding the universe. It's like in the Graal source code, the class is called Big Bang because it's sort of starting from the main method and it's expanding the universe until it cannot expand anymore. So this type of approach allows us now for your Java applications to actually figure out what parts of JDK it's using, what part of a library it's using, and what types occur in the program. What we then do offer as an option for you as well is to run some amount of initialization code during this image generation process. This allows you to potentially initialize some configuration file or similar that is then snapshotted into the final native image. An example for this is like some JSON configuration that your web server uses, and you don't want to change it. You can basically create a native image that includes that JSON configuration. Because after this whole process, we snapshot the heap and we create one final binary out of this heap that is directly executable. So the benefits here are, well, on a regular JVM, you compile the sources, and then everything happening on runtime is loading classes, loading configuration files, and running the workload. But both loading the classes and loading the configuration files is bad for startup behavior. So with native image, you have the ability to load classes up front if you want, and then already have them loaded when the application starts. And you can also push this a little bit further. You can also make your application load a configuration file or prepare a certain table before even the program starts running. So native image has certain limitations because Java has kind of dynamic behavior that makes it hard for a closed world analysis to be successful. So in Java, you could theoretically load a class file from a network stream and create it at runtime. And so therefore we offer this way where you can specify, you have to specify what is the dynamic class loading that your application is doing, and what is the reflection that the application is doing. This type of configuration can be quite complex, so therefore some popular web server frameworks like Micronaut, or most recently from Red Hat, Quarkus, have actually created some mechanisms to auto-generate those configuration files from the usual Java microservice annotations. Additionally, we are offering, we will start offering something that is actually observing the reflection and dynamic class loading behavior of your application, and then generating this native image file automatically for you. So, but if you overcome these limitations, which somebody from Red Hat, I think he said, the limitations are liberating, because they actually, I mean, it's not necessarily good practice to load classes from anywhere, and it can be also a security problem if certain reflection things are actually available that shouldn't be. But basically, if you overcome these limitations, then you get very good results for your startup time and for your memory of your applications. We have one example here that's using the native web server, and you can really see this is order of magnitude better startup. So instead of 550 milliseconds, we start up in, I don't know, 5 milliseconds. And it also gives you a lower memory usage, which is, I think, by, yeah, a little factor, maybe 2, 3, 4x lower memory. And that's because we do not need to keep all of the metadata around that the traditional JVM would have to keep in memory. And we are also not using any CPU cycles or memory for JIT compilation processes in this configuration. And for a web server application, starting up fast can be quite interesting because it allows you to scale faster at peak loads. So you don't need to worry about the time it takes to bring up your next instance of the application. And lower memory, of course, is basically equivalent to lower cost. Because if you look at the traditional, like the usual cloud providers, they charge more or less memory for memory mostly. And so this is from the Quarkus website. They made very nice statistics as well on their usage of GraalVM, and the results are basically similar as our results: order of magnitude better startup and a factor better memory usage. And what I found quite interesting here is in one of the blog posts from Quarkus was a very interesting thought here that the new metric actually for cloud applications should be not just operations per time, but it should be operations per time per memory. Because this is in the end what you pay for. You pay for how long do I use a certain cloud instance that has a certain memory capability. If I need twice the memory, my cloud instance is almost certainly twice as expensive. And in this type of metric, native images can help quite a bit because of the reduction in memory. And so this brings me to the second part of the live demo, that will now focus on native images. So what I have here as a little program, let's just cut this to be faster, is a small Java program that is listing directories. It's a small command line tool. It uses some stream stuff to list directories. And I can run this on the normal JVM, and it lists me a directory, but it doesn't feel like super snappy. And we can actually verify this by timing this. And it takes about 200, 300 milliseconds to list this directory, which is a small directory here, right? So it's really not good for a command line tool, and you can see the delay. And so what we can do now is we can now do the native image command. And we specify the class. Let's just. OK, I need to go to the GraalVM directory. Native image. There's a native image command. And I specify the class. And I run that. So this is now doing at build time a preparation of this native image for this one application. It does this closed world analysis that I was talking about that figures out all of the reachable classes. It has then sort of constructed the universe, figures out which objects are alive that it needs to put into the heap, and then finally starts the compilation process and stores then the file on disk. So compilation is finished, writing to disk, and I have now a new file, which is my list directory file. It has 7 megabytes, and it contains my Java application. So now I can use this application instead. I can just directly call it, and it gives me the same results. And more importantly, it's very snappy. So if I time this now, we are on like 9 milliseconds, 50 milliseconds real time. And not just that, if you were before looking, the user time spent was quite a bit higher than the real time here when we run on the normal JVM, because there's other threads doing compilation, etc. So you will actually have a lot of CPU cycles wasted on compiling all over again when you restart the application. So this is a small example, but we can actually also do the same thing to larger programs, like, for example, to the Java compiler. And what I have here is, I have here this, I have prepared an image for Java-C that contains the whole Java compiler. This has about 16 megabytes here. And I can just run this image with this command. There's a small difference to usually running Java-C, because I need to make sure the runtime library is on the class path. And, or should work. All right. Oh, thank you. GraalVM home needs to be set. I was just talking about that. So this goes to EE contents home. And now, yes, thank you. Excellent. Yeah, because I just talked about this. We need the rt.jar on the class path because it's not the arid runtime. Yeah, this was pretty fast. Did this thing even do something? So let's just remove this list here, that class, to make sure that I'm not cheating here. So okay, it's no longer here. I just run this. Oh, that was really fast. Oh, it's here. Okay. So yeah, that's and if I compile this with the normal Java C, then well, that was also fast, but didn't compile. This takes about 600 milliseconds real time, 1.2 seconds user time, and if I compile with the fast Java C, it takes about 49 milliseconds and 32 milliseconds user time. So it's substantially faster. So one of the things I can actually do, I will not show it now, just to show you, but I'll show you the source code here, because we are like, yeah, in terms of timing, we need to look a little bit. What I can do as well, if I want to, is I can add the ability to execute dynamically any of our GraalVM-based languages in this native image. So I can create potentially a native image that includes a JavaScript engine that is executing JavaScript. So this is similar as if you would have a C++ application, and then you embed V8 in that. So this is actually our default configuration, how we are embedding GraalVM inside the database. So this is how when we run in the database, we are doing native image, and then we are executing JavaScript there. And one of the things which is currently under development as well is to ahead of time compile GraalVM with native image before we link it with the hotspot virtual machine. We call this the libgraal configuration, and it will help us reduce the warm-up and startup times when GraalVM itself is used as a compiler in hotspot. And generally, I mean, GraalVM can be really, the GraalVM compiler specifically can be used in many of these scenarios. It can be used as a JIT compiler, can be used as an ahead-of-time compiler, can be used as an ahead-of-time compiler itself ahead-of-time compiled. And so it's a very flexible piece of software that is used in many scenarios. And we can do the native image, but we can also do the hotspot OpenJDK runtime stuff. So if somebody writes something about GraalVM, sometimes people write GraalVM and they mean actually only GraalVM native image, which is only a part of the project. And there is also others. Right, so this was the example of, this was just the command line tool. But apart from command line tool, it also can be interesting for web servers. And what I have here is, this is the hello world for the Micronaut hello world, Micronaut hello world with GraalVM. And what I did here is I have here the hello world jar from Micronaut, and I have the precompiled hello world. Let's see the sizes here. Well, the precompiled hello world has 48 megabytes with Micronaut, and this one has 12 megabytes, the jar file. But you need to, of course, think that if you create, let's say, a Docker image out of this, you will not need any JDK or JRE. So your Docker image is likely actually smaller with GraalVM and Micronaut here. And if I run this on the normal hello world, on the normal OpenJDK-based virtual machine, then yeah, it takes some time to start up. It takes 1.8 seconds here until the Micronaut web server is ready to serve its first request. So we can check that this actually works. And here we go. Yeah, so this is the default answer from Micronaut web server hello world. And if we now use our precompiled native image, then yeah, it's about 10x, no, not, yeah, more than 10x, 20x, 25x faster in startup. We can start this again. We are now at 20 milliseconds until we serve the first request. So this is kind of the setup that you don't need to worry about anymore if your server, or you can shut down your processes more often if you want, and in this way save memory. But speaking of memory, we also want to measure memory. And this is actually interesting because measuring memory is something not many programmers are doing often. And when they're doing it, they might use, I don't know, just a Java heap memory or something. But the important metric is the memory of the process. And memory usage of the process is very volatile over the time of the process is running. So it's also important to measure sort of memory over time and plot that. And one very good tool for this is the PS record tool, which is a Python tool. And what I can do here is I can first say here Java minus char hello world dot char, and I say plot rss2.png. And this is running now the process and plotting it. And I can do the same thing with my native image hello world. Starting the process, plotting it. And now I can go here and look at the Java process memory here. And we see, okay, this process was starting up here, and here it was ready to serve the first request. And when it was ready to serve the first request, the real memory usage was about 300 and something megabyte. It's quite a lot. And here we see the CPU usage, which was at 200%, 250% quite often, meaning there was more than one thread running here. And it took about here 2 point something seconds from 0 until this was finally, the initialization and all of it associated with it was finally done. And so this is, oops. Yeah, let's just, this was actually too fast for the PS record to do the right thing. Yeah, it's still too fast. Damn it. All right, I was a little bit faster with clicking, but you get the idea. So PS record basically now with the micronaut with a native image is initialized here after this 20 milliseconds, and then it's waiting for the first request, and it takes only 28 megabytes RSS size waiting for the first request. And yeah, so this basically allows you to have more instances of this application running at the same time, and allows you to scale up and down faster those instances. But yeah, so this PS record tool is a very interesting tool. I recommend using it for measuring the memory process size over time. And as I said, important metric is not just operations per time, but also operations per time per memory. So I was talking now just about two aspects of GraalVM. One was faster peak performance for Java applications on OpenJDK. The second one was better startup and smaller memory footprints with GraalVM as a native image. And this is showing another instance where GraalVM can be useful. It's on writing Polyglot applications, where you mix various GraalVM languages in the same application. So here I have a Node.js application running on GraalVM, and it is using some Java code on the side for big integer calculations, and is also using some R code for plotting. And when I have this type of application, I can run it, and it's like a web server, but the plots, for example, come from the R language. And as I mentioned in the beginning, Graal does not only support here R, JavaScript, it also supports Ruby and Python. So the Ruby team of GraalVM has Truffle Ruby, which is a very fast Ruby implementation, and we're also working on a Python implementation on top of GraalVM. And yeah, I mean, usually when you combine languages, I mean, we're not saying you should combine as many as possible. because it's, of course, not always so easy to maintain if you have an application with many languages at the same time. But sometimes, like the main scenarios are when you want to use Node.js, for example, but your core library that your company is developing is written in Java, and you want to reuse that core library. I think that's a very good use case for this technology. The other use case is, when you just basically, you just want to use a certain plotting functionality that's not available in Java, and you want to use that from one of the other languages. Finally, a lot of cloud and SaaS applications want to customize or have the need for customization, where a user is providing some script to the application, and this is sort of the standard use case for technologies like Nashorn and our technology, our JavaScript engine technology, because it allows you to make your Java application extensible with one of the scripting languages. And what we do there is we are allowing you to create sort of a context around this execution, where you can do a certain amount of time boxing, so that JavaScript that's executing is not executing sort of doing a denial of service attack on your code, and we also allow some amount of memory boxing. So our language implementations generally are just Java applications and do not necessarily need to be trusted from a security point of view, because they are also just managed. And one advantage actually of using native image, let's say compared to using C++, is that native image is still a bounce checked and managed execution. So you cannot have your traditional buffer overflow issues or similar with native image. So this allows you to execute that in sort of a bounce-checked environment. We offer this type of bounce-checked execution not just for, let's say, Java or similar languages. We also offer it for C++, where you can take a C++ or C application and run it in a managed way. So basically, if your usual C++ application would either have a security problem or would crash, we would just throw sort of a null pointer exception. So you bring the best things of Java to C++. And so that's a way in case you have sort of untrusted C++ code or C++ code that you do not want to have the ability to bring down your virtual machine, then this type of execution will help you execute that code. One reason to execute the code this way as well is the performance aspect of it, because our compiler can compile all of those languages that I've been talking about into a single executable or into a single compilation unit. So this means that if one language calls the other language, there's no overheads between them. This means if a Java application calls C++, there is no overhead. Or if a Java application calls JavaScript, there's no overhead between those languages, because we can actually compile them into the same intermediate format and then run them on the same platform. Generally, GraalVM sees itself as a sort of a multiplicative value add ecosystem, where you have language implementations on GraalVM. Some are provided by the GraalVM core team, but you also have language implementations by third parties, and third parties who are currently testing whether their own domain-specific language could run better on GraalVM. And on the right, you have the embeddings of GraalVM. You can embed GraalVM in certain databases, data stores. You can run Spark with GraalVM, but you can also run it on Hotspot or on the Node.js platform. And in the middle, you have sort of the value add of GraalVM, which is all of the common optimizations, toolings, interoperability that the GraalVM language platform uses. So in this way, we actually encourage the community to add your own language, add your own embedding, or add your own language agnostic tools to the GraalVM ecosystem. Because when you, for example, build a tool or develop a tool with the GraalVM APIs, it will work for all of the GraalVM languages at the same time. And then you can exploit this tool also with all languages in all embeddings. So is GraalVM production ready? Well, some are already running parts of GraalVM in production. Specifically, Twitter is using the GraalVM compiler for its main services. So if you're using Twitter, it is likely that your tweet is going to be processed by the GraalVM compiler. That being said, we have now released a lot of release candidates over the last year. We're getting definitely closer to production, and we'll soon be there. We are still stabilizing. Specifically, some parts of the system are less stable than others. So the core compiler parts are pretty stable, whereas things like native image is still in an experimental mode. And from the languages, JavaScript is very stable, but Ruby, R, and specifically Python are still experimental. It's a huge undertaking with a big team. The GraalVM team has a lot of engineers that are working hard to get this towards production. And we also get a lot of help, thankfully, from the community. We're actually very thankful for that. We have received a lot of people out there that have played with GraalVM, given us feedback, built the frameworks on top of GraalVM, and similar. And this is very important for a project like GraalVM, because this is the only way we can get the project to a real production state and to be then sort of the standard for executing programs, which is certainly our ambition. So here are some links for the GraalVM community. It's graalvm.org. We are on GitHub. We have lots of open GitHub issues. Please feel free to add more. And we are also on Twitter. And with this, I would like to thank you for your attention. And I'm happy to answer your questions. Thank you. Yes, I think we will get the microphone.
So, one. Thank you for great talk. It's the first time somebody replies my tweet from the stage. And my question is, as if I understand correctly, there is Graal and Graal Enterprise Edition. And Enterprise Edition is not open source, it's proprietary. And your demos were using Enterprise Edition. Are those performance conclusions also hold for open source GraalVM?
Yes, so the question is, do the performance conclusions also hold for open source Graal? We can actually check that out. It was here, right? This will show performance. And then we do Java minus char. Community, and then we do and it was objects hash that abstracted, I think. Looks good. That's a short answer. So I tested your example also with Community Edition, and it's significantly faster than not using Graal, because if you use here the hotspot compiler, it is a lot slower than our Community Edition. So so generally, our aim is to make the Graal Community Edition the best performing runtime out there. So we are committed to make sure that we are best on Community Edition. That being said, we do offer the Enterprise Edition that has additional performance on top of that. And yeah, it is a large project that requires a lot of engineering efforts and a lot of sort of force behind it. So it is the type of project where having an Enterprise Edition definitely helps making it long-term viable and bringing a lot of investment from the company's side to that project, right? So that being said, we are committed to also make Community Edition fast. and we will improve the performance of both. And currently, for example, Twitter is using only the community edition at the moment to get their speedups. So if you're using Scala programs, for example, the community edition is across the board faster than any other alternative out there. And so the Enterprise Edition is free for evaluation, so you can download it and test your programs with it. So it's free for any evaluation type of use. It's only production use that would require a license. But usually our aim here basically is to reduce your cloud bill, meaning if you are running your application on a cloud provider and it runs faster because of Enterprise Edition, then we would like to basically take a share of your savings. And that's the aim behind Enterprise Edition and Enterprise Edition pricing in general.
Yeah, you showed the native image tool and you created a native image which also used part of the standard class library, which itself has native parts. So my question is, do you have implementation of these native parts in the native image tool in the substrate VM, or do you link against the native libraries of the OpenJDK class library?
Yes, so the question is, do we link against native libraries of the OpenJDK class libraries or have our own implementation of all of them? We do link against native libraries of OpenJDK where appropriate. There is sometimes substitutions we apply, but generally we try to link against existing native libraries for compatibility reasons to make sure that we are not, it's otherwise too much effort to be 100% compatible. Because generally our aim with native image definitely is to be 100% compatible, meaning any Java program that runs on native image runs on any other JVM as well. So compatibility is very important for us, and so we are therefore relying on OpenJDK native libraries.
Thank you for the talk. A little bit different question on the native languages. You outlined C++ and you outlined C and C++. And my question is about roadmap for the native languages and slightly different languages for high performance for GPU. Did you consider OpenCL and CUDA, and what's your actually expectations for the challenges of supporting them?
Mm-hmm. So what's the challenges of supporting OpenCL and CUDA? So we had a project that was trying to run arbitrary Java code on a GPU. It was, I think, sponsored by EMD at some point. But that project didn't reach maturity. We do have some research projects that are offloading workloads to the GPU. So we do have some, if you look at our publication page, there are some research projects that aim to do that. Our current thinking is that we will support this type of offload at some point, but it will take us maybe a couple more years before we figure out sort of the right abstractions to do this offload. We are also working with some researchers, also from major GPU companies, on making sure that GraalVM performs well on these platforms. That being said, one of the things we will support as well, which is currently under development by the Graal Python team, is to support TensorFlow via Graal Python. But we are not just focused, we are focused on getting sort of the traditional GPU offload supported with TensorFlow and similar, but also maybe go beyond that and have a more tight integration. Because one of the things that we offer is we offer this way to abstract memory layouts for objects. This is how we efficiently embed in the database. And this is also how we can efficiently make sure that the data structures we are processing are GPU friendly. And we are currently developing like a framework that is trying to make the data structures work with GraalVM, but also make them friendly for GPU offload.